All right. Today we'll talk about wind energy. Okay, so what we're going to do is use moving air, that is wind, to produce electricity. Okay, so that's the goal. Electricity is a convenient form of energy because you can transport it across the country very easily. Things run efficiently on electricity. Okay, so your Tesla runs at a 90% efficiency. What does that mean? 90% efficiency on an electric car.
Out of 100% of the energy that goes into it,
Mm-hmm.
it uses 90.
Yes, so if 100 joules of energy is stored in the battery, 90 joules can be converted to motion. Whereas your gas car, if 100 joules of gas is pumped into the car, only about 20 joules can be converted to motion. Okay. All right, so we want to produce electricity and we have various techniques to doing this. Today we'll learn one of them. All right, well, I will go back to this simulation. And so what is it that you're doing? Okay, so here's magnets, here's a wire. If you turn this wire between the magnets, you produce electricity. And the way it is connected, so now you gotta turn this wire. It takes energy to turn the wire, okay? And you just gotta figure out a way to turn this wire. And today what we're going to do is, in a windmill, we're going to use a windmill to turn this wire, okay? So this is what's inside a generator, okay? And we're going to use a windmill today to turn this wire, okay? So now let's go look at the details. Everybody understand what we're doing? Okay. All right. All right, we've had enough of you. Okay, so we've been using wind energy for a long time. Okay. So again, what do you mean by wind energy? What do you mean by wind energy? Okay.
Energy created by wind.
Not created in the wind. Okay, so whenever something moves, okay, so if so the air in this room is still, so it doesn't have any kinetic energy. Okay, so whenever something moves, and let's say this is the mass density of air. Rho is the mass density. What does that mean? Mass density? 1 meter cubed. 1 meter cubed. That computer Carol, that's 1 meter cubed. And that much air weighs about 1 meter cube of air weighs about 2.5 pounds. That much air weighs about 2.5 pounds. Okay, and so when the wind is blowing at speed v, the kinetic energy contained per unit volume is 1/2 rho v squared. You don't have to remember this formula, but that's the energy contained in it. Okay, so this moving air, what we're going to do is we'll get the moving air to turn blades. And what are these blades going to do? I'm sorry? Yeah, the blades are going to spin, but that's not our end goal. What is our end goal? You got the moving air to spin the blades, and that blade, we're going to use gears to connect it to that wire in the generator. We're going to turn that wire. And that's how we're going to produce electricity. You guys understand? All right. All right. All right, but historically we've been using wind energy, so blowing wind to push boats and stuff like that. And here's pretty amazing thing. And they have these things you can ride these things in St. Augustine, by the way. So this guy has 11,000 horsepower. This thing, the sails could generate 11,000 horsepower. Okay. Now if you drive a small car, most small cars have about 110 horsepower or whatever. So this is the same power as 100 small cars. Yep. So you can generate quite a bit of power. So here's the blowing air turns the blades here, which will turn a grinder. So you could grind grain in this windmill. We've been using wind power to do this. This thing is pumping water. Okay. So we've been using windmills for quite a long time. Okay. Well, how much wind energy is out there? Okay. So one of the first questions we want to answer is, do we want to bark up the street? Okay. So for instance, so this is the amount of power needed to run the world. So this is how much, okay, that's 16 terawatts. 16 terawatts is 16,000 gigawatts, okay? And this is a Hoover dam, okay? So you know that we've learned that we need 16,000 Hoover dams to run the world, 24/7, okay? So 16,000 Hoover dams running 24/7, 365 is what's needed to run the world, okay? Well, there's plenty of wind blowing. You could run the world just on wind. Okay. You see, you couldn't run the world on tidal energy. You know. You guys have heard of tidal energy? Okay. So when the tides come in and go out, what you can use is the motion of just like you can use the motion of the wind, you can use the motion of the tides to turn that wire and produce electricity. But you can't run the world on tidal energy. You couldn't run it on geothermal energy. We'll talk about that, okay? But so these are all niche solutions. If these solutions are like, if you are walking on the sidewalk and you see $10 lying on the sidewalk, will you pick it up? I'll pick it up, yeah, you know. So that's the kind of stuff. If there's free money available, you'll take it, okay? But this is not going to pay your mortgage, okay? This can pay your mortgage. And this can certainly pay your mortgage. Okay. But the point is, so you can run the world on sun and wind, okay, easily. Okay. Yeah. So by the way, today, because we are using a mix of 80% fossil fuels and 20% renewables, see, whenever you use fossil fuels, you're wasting a lot of energy. Okay. Whenever you use fossil fuels, you're only using 1/3 of the energy on the average. Okay, so you need about 18,000 Hoover dams to run the world. But if you were producing electricity using solar and wind, all you need is 12,000 Hoover dams to run the world, because there's no wastage of energy. And when you produce electricity, everything runs more efficiently. Okay. Okay, so you know all of this. In 2050, we can run the world on 12,000 Hoover dams when all of the energy is being produced by wind and solar. Okay, almost all of the energy. So again, according to these fellows, about 40% of your energy will come from wind and about 60% from solar. Okay? With current existing technology, you don't have to invent new technology. Okay? So the future looks good for you guys. Yeah. Do you guys know why did we use fossil fuels the past 50, 100 years?
Cheaper,
I'm sorry?
cheaper.
It was the cheapest thing. Okay. All right, so that's what we use all the time. Yeah. It's like saying, if you had to buy 1,000 burgers, are you going to buy expensive burgers? No, you're going to go find the cheapest burger. Okay. Right now, wind and solar are the cheapest source of energy. Okay, so what this tells you is cost per megawatt hour. This is what it costs FPL and all that. Okay. Do you guys know what a kilowatt hour is? Okay, this is a unit of energy. This is what your electric bill is based on. And go look at your electric bill. This thing costs you about 15 cents, 12 cents, let's say. Okay. So now this in different places the costs are different, but roughly for coal, that's $100 per megawatt hour. So a megawatt hour is 1 megawatt hour is 1,000 kilowatt hour. Okay. Mega is a million. Okay. So and this is 1,000 kilowatt hour. So if you divide this by 1,000, if you're producing electricity by coal, it's costing FPL, according to this, 10 cents. And they're selling it to you for 12 cents. Now this, I guess, but we give them subsidies and all that. Anyway, this is sort of rough estimate. With wind and solar, it would cost them, see, that's about 50 cent, $50. You guys following this? If FPL produces electricity using wind and solar, it would cost them 5 cents. And they can sell it to you for 12 cents. So if you're a CEO of FPL, what are you going to do? Produce your electricity using wind and solar, or? Of course. So what's the problem? What is holding us back? You guys understand what I'm saying? You can make boatloads of money. The main thing holding back their widespread adoption is cheap batteries and smart grid. FPL promises you uninterrupted power all 24/7. Okay? So unless if batteries become cheap enough, then fossil fuels are out the window. Okay? No amount of political support can I mean, you can't have any political support for it. Yep.
When you say smart grid, you mean the infrastructure to actually put power itself?
Well, smart grid, one of the features for it would be okay, so smart grid will have a couple of important features. Okay, so right now we don't have this. So let's say you put solar panels on your roof, okay, and when you feed the grid back, okay, here's a feature that you can understand. Now, the power usage in the middle of the day is the highest. Okay, so if we want to control the usage at that time, we want to be able to price it at the time of day. So if you use electricity at noon, then it will cost you 18 cents. But if you use it at midnight, it'll cost you 6 cents. Okay? We don't want you charging your Tesla car, your electric vehicle in the afternoon. We want you to charge it at night. Okay? So smart grid will do all of that. Okay? It also, the grid will have battery storage. Okay, so if a nuclear power plant is not producing enough electricity, the battery will provide power, and the battery was charged using solar and wind. Okay, so you'll have real-time metering, two-way metering, and all that kind of stuff in the smart grid. Okay. All right, so we already know renewables can already produce the cheapest electricity. Okay, what's preventing us from widely adopting it is storage. Okay. Yeah.
I thought it was because we didn't have cheap batteries.
Yeah, that's storage is cheap battery. Storage is battery. Yeah. All right, so this fact, okay, that wind is the cheapest, it's been the cheapest for a while, okay. See, the wind has been cheapest for a while, you can see that. And once it's the cheapest, we've been putting more and more windmills. And here's the evidence. Well, so this is the total installed capacity. By now, there's 1,000 Hoover dams worth of wind capacity installed in the world. Okay. If you were running the world entirely on wind and solar, how many Hoover dams do you need? 12,000. Right. You already have 1,000 worth, and this is just wind. Okay. And there's, I believe, close to 1,000 of solar as well. Okay. All right, so we're getting there. Global wind capacity has increased by 14% annually. Installed capacity has increased by 14%. Your S&P 500 hasn't increased by 14%. Okay, so why is that happening? Again, because of the low cost. Okay. So we are installing more and more wind capacity. Okay. In the US, more than 60,000 windmills are there currently. Okay. And so might be a couple of years old information. Okay. With a cumulative capacity of 122 gigawatts. Okay. And now let me think about this. Let's say I gave you money to build a Hoover Dam. How long will it take you to build a Hoover Dam? It's very expensive. There aren't good enough locations to build it. Okay. And then it'll take years and years, 10, 20 years to build a Hoover Dam. I give you the same money, in 6 months you can put up the windmills. You guys understand? Yep. So wind capacity increased from 2010 to 2020 by 12% on the average. Yeah. Wind per capita. Okay, what does this number mean? So wind energy produced per person living in that country. Okay. In the US, on the average, a household runs on 1,500 watts. Okay. So this is the power consumption on the average per household. And let's say if there are 2 people living in a house, so 750 watts is needed to run per person a house. Okay. What this number says is Denmark has by far the highest installed capacity per capita. Okay, in Denmark, the wind capacity is such that for every person living in Denmark, 800 watts of power is produced by wind. Okay. So the US lifestyle could be maintained. All the houses can be powered in Denmark just by wind. Okay. Much of Denmark's wind capacity is offshore wind farms. All right, so now the idea is the following. You have a parcel of a river of air flowing, and you want to capture this energy. Okay? Now, if this air is moving, let's say 20 miles an hour, and you can somehow stop it, and capture all that energy, that's 100% you've captured. Okay? What gets the air moving? I'm sorry? Heat from the sun is what gets. So essentially you are harnessing solar energy. Okay? So you want to harness this energy. What do? You put a fan on the way. So you put this blades in the way. Okay? And some of that energy gets transferred to the rotation of the blades. And the stuff that you cannot capture, the wind is slower downstream. Okay? So the question is, what is the best you can do? And the best you can do is you could capture 60%. Okay? That's the limit. So you could capture 60% of this energy. So 60% would go there, and 40% would, just be left on the table. Okay. Now, in practice, only about 40% is captured. Okay. So this, on practice, 40% is captured and 60% is gone. But we are happy with that. Why are we happy with that? It's free, and we're picking up 40% of it. Okay. And what is for your generation, what is the best thing about it?
No carbon dioxide.
No carbon dioxide. Very good. It's free, no carbon dioxide, zero, almost zero environmental impact. Yep. All right, so now here's a very important point. Power in wind is proportional to cube of wind velocity. Okay, so here is a wind velocity. Okay, so power is proportional to wind velocity cubed. Okay, what that means is if you double the wind speed, the power increases by a factor of 8. Did you guys understand that? Okay, so let's say if the wind is blowing at 5 miles an hour, you're getting a certain amount of power. If the wind blows at 10 miles an hour, you're getting 10 times the power. 8 times the power, but we'll say 10. Okay, so 5 miles per hour versus 10 miles per hour. Here is the power. This power is 8 times as much. Okay. So why am I saying this? Okay, so when you put your windmill, where are you going to put it? You're going to go look for the location where the wind blows the hardest. I mean, that's a easy thing to figure out. But you want to make sure that it blows the hardest and for the longest. Okay. If it blows someplace, it blows at 8 miles an hour, but only for 2 hours, and somewhere else it blows at 7 miles an hour, but for 10 hours, then you put it there. So you want to figure out where the most energy is blowing. Okay. So we'll come to that. Okay. You want to understand this tip speed ratio. Tip speed ratio. When they say tip speed, what they're talking about is when this blade is rotating at this, they're talking about the speed of this tip, okay, the windmill tip, okay. All right, now here's the deal. So here is wind blowing. Here are the blades. I'll put a different color. Here are the blades. Okay, so this blade is rotating this way. When this blade rotates, it creates turbulence. Okay, and now you don't want this blade to go through the turbulence. Okay, so if this blade goes through the turbulence, it can't capture energy efficiently. Okay, so what you want is for this turbulence to blow away and this blade to go pass through clean air. Okay, so you guys understand now that you don't want the blade spinning too fast. Okay, so blade spinning too fast is bad. Okay, what happens if the blade spins too slow? So if this blade goes by, here's this turbulence, it gets blown away, but this guy comes by 3 hours later, you wasted all the wind energy. Okay, so you don't want to go too slow. If you go too slow, you're letting all the money pass by. Okay? If you spin too fast, then you're going through turbulence. Okay? So, if a blade spins too slow, then most of the wind will pass by the rotor without energy being captured. On the other hand, if the blades spin too fast, then each blade will always be traveling through turbulence of the blade in front of it and not capture energy efficiently. Okay? So, for this reason, tip speed ratio is the most relevant parameter in determining the efficiency of a turbine. Okay, you want the turbine to capture as much energy as possible. Okay, and so the tip speed ratio for the turbine should be appropriate. Okay, so So it's important that just enough time lapses between the two blades traveling through the same location, so that new unused wind. Okay, so okay. Huh. I don't even define tip speed. So tip speed ratio is the, I'll have to fix this, is the ratio of the tip speed to the wind speed. Okay. I'll have to fix the notes, but anyway. Yep.
Is that, so what is, so is it by the angle of the blade is what determines the tip speed? Like, how does that control?
No. Oh. I guess you could.
The design of
Because
the
you want
blade, like
the-
aerodynamic design.
No, what is, so the tip speed is the speed of the tip rotating blade. And that depends on the size of the blade and the rotation speed of the thing. And yeah, well, so the rotation speed depends on the dynamic thing. But once the wind is blowing, I mean, you want to turn as fast as possible. Okay, so okay, ask your question again.
No, is it, like, is it determined by the angle of the blade? Does it work like a propeller in a plane?
Yeah, it's like a propeller in
It's like
plane.
capturing air going past it, right?
Well,
The angle of the blade
okay,
would
so
affect the speed.
so that question. So let's say the wind. So if the wind is blowing at 10 miles an hour,
Right.
and now your goal is at that wind speed, you want the propeller to turn as fast as possible. Okay, that's where the airfoil design goes. If your propeller is turning as fast as possible, then you're capturing the most energy. Okay? But you don't want to be turning so fast where you're going through turbulence. That's all. Okay. Yeah. Mm-hmm.
Is the propeller turning based on it catching air, or is it turning based on a motor turning it to match the speed of the wind?
No, well, so let's say if the wind is blowing this way, you put an edge like that, you won't turn at all. So you have to design the propeller the right way for it to turn. So you can have an orientation where you don't even turn. And they can do that if wind speeds are during hurricanes and stuff like that, you don't want the blades to catch any wind because you would do damage to that. So you can apply brakes. Okay.
So it adjusts based on conditions.
Yeah. Mm-hmm. But I mean, your ultimate goal is if you're not causing any damage, you want to spin as fast as possible, okay, without going through turbulence. Okay, so tip speed ratio is the most relevant parameter in determining the efficiency of a turbine. Again, what is your goal? Not go through turbulence and not let clean wind pass through. Okay. This picture illustrates turbulence. Okay. So there are two kinds of wind turbines. This is a horizontal axis. The axis about which it rotates is horizontal, and here's a vertical axis turbine. Okay. Now it turns out that, okay, so let me show you a graph. Okay, so here's a graph of wind speeds with elevation. Here's the height and wind speed, and you can see that as elevation increases, wind speed increases. Okay, 800 meters This is 800 meters is roughly, when those embry-riddle planes fly in a pattern to come into land, that's roughly how high they are. Okay. 800 meters is 2,500 feet. Okay. So you see wind speed increases with height. So what you want is, so your windmill to be as high as possible. Okay. Now, you can, if you have a horizontal axis, if you have a windmill like this, you can make a tall tower and you can construct a windmill like that. If you have a vertical axis windmill, it's hard to put this on a tall tower. Okay, so that's why you don't see windmills like this, a lot of them. Okay, so you want your windmill to be at a high tower. The advantage this guy has is, okay, the wind direction changes. So right now the wind is blowing this way, and so you have to face the wind. But if the wind is blowing this way, you have to turn this guy to face the wind. Okay. This guy you don't have to turn. The wind can blow in any direction it wants, and it'll always capture wind. Except that you can't put this on a high tower. Okay. All right, so this is a vertical axis windmill, and this is a horizontal axis windmill. Okay. All right, wind turbines have short construction times and are small compared to other types of utility-sized generators. Okay, utility-sized generators are, something that can produce as much electricity as a Hoover Dam. Okay. A 10 megawatt wind farm. Okay, so right now, large windmills, a single large windmill can produce 10 megawatts. So to build a Hoover Dam, all you need is 100 of those. Easy. Yeah. Can easily be built in 2 months. Okay, so you can just plop a Hoover Dam in 1 year without any environmental damage. Okay. That's a great thing. A large 50 megawatt wind farm can be built in 6 months. Wind complements solar energy well. Days with little sunshine are usually days of better than average wind. Okay, so wind and solar complement each other well. Okay. So wind turbines come with horizontal axis and vertical axis turbines. So this is a horizontal axis, here's a vertical axis. Vertical axis motors have advantages that they do not have to turn with changing wind direction. Their generators and gearboxes are mounted on the ground, which is easy maintenance. However, they're difficult to put up on a tower to take advantage of higher wind speeds. Okay, so you can't put them up on towers. Okay. All right, so here's a 2 to 3 megawatt capacity. This is what you'll see, but the newer ones, so the largest current one is 13 megawatts, which is an offshore windmill being put up in England. Okay. So this is 2 to 3 megawatts. So let's say this is 2 megawatts. You would need 500 of these to make a Hoover Dam. Okay. This is where the generator and the gearboxes are. What is the generator? That wire that's turning between magnets. Okay, and to scale, here's the person. Nacelle is what this is called. Okay. The electric generator, along with the associated drive systems and gearbox to match the rotating speed of the wind turbine, are contained in this housing. Okay, so the generator and the gearbox are contained. And I'll tell you what the gearbox does. Okay. All right, so the blade rotates. The wind makes the blade rotate. The rotor rotates at the same speed as the blades. Okay, so in a large scale turbine, this is typically rotates at 20 RPM. So this is rotating roughly at 20 RPM, 20 revolutions per minute. And that's the rate at which the shaft rotates. Okay, but that wire inside the generator, everything good? Okay. This wire inside the generator, that wire has to be rotated about 1200 RPMs, 12 to 1800 RPMs. Okay? So the blade is rotating 20 RPMs, and then you got to speed it up, and that's where you need the gearbox. Yeah. So the low speed shaft is connected to a gearbox, and the gearbox increases the rotational speed of the shaft to 12 to 1800 RPMs. This is required rotational speed by most generators to produce acceptable levels of power. Okay. So that wire needs to be rotated. That wire needs to be rotated 12 to 1800 RPMs. Okay. You guys understand? Okay. Now here's the deal. Mm. The generator in the wind turbine produces AC current, AC electricity. Some turbines convert this AC to direct current and then back to AC using an inverter. Okay. So you missed out on the donuts.
Oh man.
Yeah, we
It'll be
bought
fine.
we bought donuts and everybody had donuts. So the windmill produces AC. Then you convert the AC to DC and then back to AC. Sounds like you're wasting money. Why would you do that?
What's, oh, dry current.
Mhm.
Just kidding.
So if you do something, you obviously do it for a good reason. Yeah. So we're going to figure that out. So the windmill produces AC, then it's converted to DC, and then AC back again. So here's the deal. You guys understand the issue? Okay. So here's Hoover Dam, here's your nuclear power plant, here's a coal power plant, here's a windmill. They're all connected to the grid. Okay, so you're putting electricity in this grid. You're feeding electricity into this wire. Okay. Now, in this wire, if the electricity is flowing like that, if the electricity is flowing like this, and what you get out of your wall socket is 60 cycles. There are 60 of these per second. Okay? The frequency is 60 cycles. Okay, so you saw that when the windmill, that thing could be rotating anywhere between 1200 and 1800 cycles. So that could be producing 1200 to 1800 hertz signal. Okay? And all these guys, when they feed electricity into the grid, they have to match exactly this. This is how you have to feed in electricity into the grid. Every one of them have to match the waveform on the grid. So that's why you have to convert this to DC and then back to AC with the 60 hertz signal that exactly matches that. Okay, do you guys understand? So that's why you have to do that. All right. So by converting the variable speed AC current produced by the generator to DC current and then back to AC, the electrical signal is converted to match the phase and frequency of that on the grid. Yep. Here's another thing about the electric grid. Okay. There's exactly how much power produced as is being used. Okay. So if you turn off the lights, we've said this before, you go get up and turn off the lights, that much electricity production has to decrease at that instant. Yeah, it's absolutely amazing. Okay. And part of that is, so you have to match, to be able to do that, you have to match the exact phase like that. Okay. All right, but anyway, all that is technology that we know how to handle. Okay. So that's one of the things about renewable. It's intermittent and so on. Okay. And so cheap batteries would help us solve all those problems. All right, so here's a moving parcel of air. The energy content of that air is, again, you don't have to follow this, you don't have to, I'm just going to quickly go over it. The energy content of this air is the volume of this packet. Here's D is the size, that's the volume of the cube, and that's the energy per unit volume. Okay, so that is the energy of the entire packet. Power is energy divided by time. Okay, power is how long did it take for this parcel to pass this location, and that would be, the velocity is d by t. Okay, and so one of the d is taken divided by t gives you velocity. So it's velocity, the power is dependent on velocity cubed. Okay. And we said that speed cubed. Power per unit area. So here is 1 meter square. So what we're asking is, here is 1 meter square. How much wind energy is passing per second per meter square? Okay. Why do we need to know that? If you want to capture more energy, you want bigger and bigger blades, so you can capture more and more energy. Okay. So here is a meter square. 1 meter is roughly 3 feet. Okay. And what you want to know is, so power per unit area, how much energy is passing per second per meter square. Okay. Yes. So joules per meter square per second. Okay. And power per unit area is proportional to speed cubed. So you double the speed, the power increases by a factor of 8. Okay. And so power per unit area is given by that. So when wind speed doubles, the power available is increased by a factor of 8. Okay. So again, wherever you want to put windmills, what you want is high winds, steady winds, and that's what you're looking for. And that's what happens offshore. So that's the best place to put windmills. Okay. Offshore wind farms are the best location. Okay, so here in the US, so all this information is very important and very useful, and so that's why they've measured these wind speed. The central parts of the US are great locations for windmills, wind farms, and offshore wind farms. Okay. These are the best resources, locations to put windmills in the US. Okay. All right, so again, the power is proportional to the power of speed cubed. Okay. Since the power output for a windmill is strongly dependent on wind velocity, choosing the appropriate site is extremely important. Wind velocity increases with height. Okay, you saw that. Wind velocity increases with height. So what you want to do is make this tower as tall as possible. Okay. So the blades can capture as the blades are capturing high-speed winds. Okay. What is the price you're paying? Maintenance costs are a little higher. Yeah, you got to climb up higher and stuff like that. But if you capture more energy, let's say you capture $20 worth more energy by building a higher tower, and your expenses go up by $5, you're going to build a higher tower. Okay, and that's what. You know. So wind velocity increases with height as friction between moving air and the ground is eliminated. So at low levels, the friction between air and ground prevents it from moving fast. Higher you go, the less friction there is and the faster wind blows. Okay, so wind speed increases substantially with increasing altitude. Thus, locating the turbine at the top of a tall tower is advantageous. So there's a trade-off between power output and cost and serviceability of a unit. Okay, so what this tells you is, okay, the Betz limit is the highest amount of energy you can extract from moving air. And we have already said that that's about 60%. And this graph shows you, what this graph is showing you is the following. Here's the wind speed, and here's the wind speed before it hits the windmill, and here's the windmill, and V naught is the speed after it's passed through the windmill. Okay, so you see rotor efficiency, how much energy can it extract, and the maximum is 59%. Okay, so that's what this is, the Betz limit. Okay. Actual windmills extract about 40%. Okay. All right. Okay, so what this shows you is, with tip speed ratio, it's showing you a windmill with one blade, how much energy it can extract. The best it can do is about 40%. Okay, and this would work well in very high speed winds. A two-blade rotor works well in these wind speeds, and that's how much energy, that's the best it can do. A three-blade wind rotor works well in these wind speeds, and that's the best it can do. Okay, has anybody seen a one-blade or a two-blade windmill? No. Okay, so the reason we don't see them is because they're not stable. They wobble a bit. Okay, and so that wouldn't last a long time. You would cause damages. This guy is the best compromise. This guy doesn't wobble. And if you had more than three blades, then you're not capturing, because of friction and stuff like that, you're not capturing as much energy. So the three blade is the best compromise between high energy yield, stability, and durability. Okay. So that's what you see all the time. The best actual efficiencies for a high-speed two-blade design are 45%. So in practice, a two-blade can be 45% efficient, and the three-blade is about 40% efficient. Okay. But the two-blade ones are not stable, so we don't build them. Okay. Two-blade turbines are prone to gyroscopic precession and resulting in wobbling. Any number of blades greater than 3 would create greater wind resistance, making them less efficient.
Why would they even make the one with two?
Well, I mean, when we were testing them out to see if 2 were more efficient, so they did try out two-blade ones. They are more efficient, except that this, the wobbling is why we don't build them. We're always looking to do the best we can for the least amount of money. We're always looking for, I mean, this is when you're investing trillions of dollars, you want your money to work as efficiently as possible. Okay, so this is cut in speed. So if the wind is blowing slower than this, the blades will rotate, except that remember what is it that you want to do? What is it that your ultimate goal is? To turn that wire between the magnets. And you want to turn that wire like 1200 to 1800 RPMs. Okay, so if the wind is blowing too slow, then you can't turn it at that speed, so you're not producing useful electricity. And cutout speed is if the wind is blowing faster than that, you don't want to do damage, and so you put on the brakes. Okay. But nowadays you have better and better design where you can have the windmill operating at higher and higher speeds. Each location has a well-defined distribution of wind speeds. Okay, so every location has this. So if you're thinking of putting a windmill in a certain location, the first thing you do is measure this, okay, the probability curve versus speed. Okay. And this is given by the Weibull distribution, the wind speed. Okay. So you measure this wind speed distribution. Now here's the deal. So here's the wind speed distribution at a given location. Okay. Here's the frequency. So at this location, at some given location for 500 hours, it's blowing at 5 meters per second. For 400 hours, it's blowing at that speed, and so on. But remember, so here's 5 meters per second and 10 meters per second. When the wind speed is twice as much, the power is 10 times as great. So even though it's only blowing for 200 hours at 10 meters per second, that's when most of the energy is you're getting most of the energy. So most of the energy is produced at high wind speeds, which is only for a few hours. So here's your windmill standing there for 24 hours. Here's the windmill standing, and it's producing almost all of its energy within a couple of hours. But you need electricity 24 hours. Okay? So you produce that electricity in 2-3 hours, and then you need the battery, so you can charge the battery. Okay? So that's the issue. Did you guys understand that? Go ahead.
Can, so, like the solar towers that we learned about last week,
Mhm.
can it kind of like harvest the energy to keep things going? Does
Mhm.
that make sense?
Yeah. So wind and solar complement each other. When the sun is shining, the wind is not blowing in. Okay, so you can produce electricity using wind and solar, but still, it's not exactly matching the usage. Okay, so you do need batteries.
Okay.
Okay. So in an ideal world, in an ideal world for our children and grandchildren and stuff like that, what you need is everything to be cheap. These two are already cheap. And if this guy is cheap, then it's heaven on earth. Okay. Environmentally, anyway. Yep.
Can you build a solar farm in the same place that you build a
Yep. So you can do multi-use. You can build windmills and have cattle ranches. You can build windmills and have farming and stuff like that. Yeah. All right, so let's say you have $3 billion, you're going to build a wind farm. Okay? Just like planting trees when you're farming. So the spacing needs to be 3 to 5 diameters. The wind is blowing like that. And this needs to be 6 to 10 diameters. Yeah. Why is the spacing? What determines the spacing? this is turbulent air. What you want is clean air flowing through this. So that's why that distance, okay? And turbulence is downstream and on the side as well, um, so that's what determines the spacing, okay? For wind farms, the relative placement of is important. If they're too far apart, then the facility will occupy more land area than necessary. If they're too close together, turbulence from one will affect the other turbine. Okay. Yep. Mm-hmm.
Earlier you stated that the wind farms do better like offshore.
Mm-hmm.
So about how far offshore would you say that the wind farms are?
Probably about 5 to 10 kilometers.
Okay.
Mm-hmm.
So like if you were fishing, you would be able to see them like in Florida?
Mm-hmm. Well, we don't have them in Florida yet.
Oh, okay.
I don't believe so.
Okay.
Mm-hmm. How many of you guys are against offshore wind farms or for them? Are you for them?
Why not?
Hmm?
It's fine.
Mm-hmm.
I think it sounds pretty good. They're not heating up the water around them to cool off or anything, messing with the ecosystems.
But there's like underground cable, you have to get it to like a substation on the grid, like on the mainland.
Yeah, well, they're built, so if you send me an email, I'll send you an article. They're building a 3,000 kilometer underground cable. They're going to produce solar electricity in Morocco and going to feed it to England.
Bless you.
What's that? Bless you.
Thank you.
All right, so the U.S., they're the good sources of wind energy in the U.S. Okay. All right, so here's onshore versus offshore. Placing wind turbines a few kilometers offshore can provide about 50% more energy. The same turbine. Okay, so you put it onshore versus offshore. Here you're producing $100 worth of electricity versus $150 worth of electricity. Go ahead.
So I obviously missed the beginning part of the.
I'm sorry?
I said I obviously missed the beginning part of the session.
And
but
the donuts.
But there's a cable that goes to these wind farms offshore.
Yeah, it's no big deal.
Like how big are these cables though?
As long as it gets from the,
Hmm.
Like in diameter though. Like
depends. Depends on the conduit, what they're doing, how much cable's already down there, if it's new, or if it's, they're using like existing stuff, and how big they're tunneling, trenching. The wires itself probably aren't that big.
Oh, you don't recognize me? So Morocco, so here's the cable. Going from Morocco to, so here's Morocco. So I can send you this. Anyway, I was trying to figure out, see the length of this cable. I don't see it. So 4,000 kilometer subsea cables are going to bring power from Morocco to England. And there's the cable. So it's nothing if you have a few kilometers of it. All the technology is here. Again, what is stopping?
Money.
No, cheap batteries. Okay. Offshore windmills are currently placed in depths of 40 to 50 kilometers. 40 to 50 kilometers is about twice the height of that health science building across the street. Okay?
It's a meter.
I'm sorry?
It's a meter.
Yeah. So that's building is about 20 meters high. Yeah.
Why don't they build it in a grid shape?
I'm sorry?
Why don't they build it in a grid shape like they do the onshore ones?
Oh, this is determined by the depth or what? Yeah. Yeah, and I mean if you're putting 100, then this is better than putting 2 lines. Okay. So the biggest wind turbine is going to be in England this year, 100 miles off the coast of northeast England. The world's largest wind turbine will start generating electricity, and it's about this high. Okay. The best way to harness more wind energy and at a cheaper price is to build bigger turbines. So you're capturing more wind, and the taller you are, the higher the wind speed. So the bigger is, you're getting more bang for the buck. Okay. And that's what the idea is. Capacity factor. The capacity factor is, so what is the maximum energy power you can produce? Okay. And what are you actually producing? Okay, so let's say, so for a windmill, here's how you would calculate it. So the maximum power, let's say, is 1 megawatt while the wind is blowing the fastest. Okay, but the wind is not going to blow at that speed all the time. Okay, so most windmills are working at about 35% of the capacity. Okay. Offshore winds are generally stronger and steadier than on land, and the capacity factors are higher on the average. Okay. Floating offshore wind technologies could greatly expand generation potential, as 60% of the total wind resources in the US lie in depths greater than 60 meters. So in deep waters, that's where our most wind potential is. So we want to build floating windmills on floating platforms. Okay. And here's the advantage. The second advantage is then nobody will complain that it's ruining their view, because it's far, well, up in the Northeast, that's what they have against windmills.
Can you see them like up north? Like,
Yeah, well, I mean, so right now you want to build in shallow waters, so you build them close enough.
okay.
So environmental effects of wind power are almost insignificant, so no environmental effects. Okay. You hear about birds, windmills killing birds. Look at this number. Cats kill 2.5 billion birds. 2.5 billion. Wind turbines only about 250,000. Yeah. More birds die. 600 million die by running into buildings, flying into buildings. Why do they fly into buildings?
Is the glass is so
Yeah. All right. All right, that's it, guys. So I hope you guys